Hello, we'll be discussing about coupling constant and coupling between several nuclei in NMR spectroscopy in this PPT. So these slides will be explaining the spin splitting pattern observed in the proton NMR spectrum of a single or a simple organic compound. Coupling constants are used to determine which groups of protons are coupling with one another in a proton NMR spectrum. So this slide shows actually the actual appearance of the absorption base in NMR spectra. So the structure of a molecule can be predicted by NMR spectroscopy. As we know from the previous lectures, that the signals in an NMR spectrum relies on several factors. So one of the factors affecting the location of the peaks in NMR spectrum is chemical shift. The location of a peak shows the types of the protons or how many protons there are in a molecule. Also about the surrounding electronic environment. So in the first case, fluoroethane, we have got two types of protons. One it is the CH2 proton, the other one it is CH3 protons, and they are connected or they are bonded with the electronegative atom chlorine. Hence, two signals are observed. One it is for the methylene proton, which is actually said to be de-shielded, and here in the downfield we can find the absorption signal. And methyl proton, which is away from the chlorine atom, and they are said to be shielded, and whose signal is found to be upfield. Hence, the positions of the signals are decided by the electronic environment and also the chemical shift values. But in addition to knowing where the peaks are on the chemical shift scale, and also the fact that what influences the chemical shift value, one must also consider that the peaks in NMR spectrum are not always a singlet. So in this example, the molecule, as we said, there are two kinds of protons in it. Thus two signals are expected in its NMR spectrum. It has been observed that for each kind of protons, we do not get a singlet, but a group of peaks are observed. So for the CH3 protons, a triplet, a group of 3 peaks are observed, and a quartet, a group of 4 peaks is observed for CH2 protons. So what makes such splitting of a single peak into these quartet and triplet or nothing but the interaction between different types of protons which are present in the molecule will be causing a single peak to split into doublets, triplets, or multiplets. And such phenomenon is said to be spin-spin coupling phenomenon. Actually, it involves the spinning nuclei, and further, this involves the interaction between the spinning magnetic moments of different sets of protons, and that leads to the splitting of the signal into a single signal or single peak into multiplets. And here is another example, 1,1-difluoroethane, and they differ in their positions of the signals when compared to the chloroethane. CH protons, it is further moved downfield as it is highly de-shielded. And this is shielded, and again it is found in the upfield positions. And the CH proton, which is connected with the CH3 protons, that is 3 protons. So the signal of the CH proton will be quartet. And CH3 proton, which is bonded with 1 proton, hence the signal for this CH3, that is the methyl group, will be of doublet. So how does this splitting occur? That will be discussed in the coming slides. So here the slide explains the cause of the spin-spin splitting, and for which we are taking two protons HA and HX, and we will be discussing about the effect of the HA spin on the spins of the HX and how does the splitting occurs. So the two hydrogen nuclei HA and HX, which are sufficiently close together in space in a crystal lattice, and then they exert an appreciable magnetic effect on each other, probably 0.01 microtesla. And let us just ignore for time being the directions of a HX nuclei right now. Only we'll be considering the Z component of the HA spin, and that will be showing two possible directions, and one it is upwards and the other one it is downwards. So the two possible directions, one it will be along with the applied field direction V naught, and another one will be opposing the applied field direction B naught. But the lines which are originating from the top, the HA, which are considered to be the bar magnet, opposes the applied magnetic field direction when HA will be up, and this happens near the HX protons. Similarly, the lines originating from the A when it is pointing downwards at HX, these lines of forces actually reinforces the applied field. So the nucleus HX in an applied field thus experiences with equal probability two types of net magnetic field. One it will be reduced by dA, the other one will be increased by dA. So when this HX nucleus experiences more magnetic field, then it will be dA plus d naught plus dA, and if it is experiencing less net magnetic field, then the magnetic field will be d naught minus dA. And HX nucleus of a sample shows two different resonance positions in the spectrum. Thus, the spectrum will be showing HX signal to be a doublet. And that doublet is due to the influence of the HA proton on HX proton. Similarly, the effect of HX proton on HA proton also causes the A signal into HA signal into doublet. Here comes the coupling of the hydrogen nuclei, which are directly bonded, and also when the hydrogen nuclei are attached to a third non-spinning nucleus. So how the magnetic effect, the interaction of the magnetic effect between the two protons are transmitted. In general, they are not transmitted through space, but instead they are transmitted through the bonded electrons. So the spin-spin coupling effect occurs through the interaction of the nuclear spins with the bonding electron spins rather than through the space. In other words, the mutual magnetic influence between the two protons, HA and then HX, is not transmitted through space but through the electrons in the intervening bonds. So here hydrogen nuclei joined by a pair of electrons as in H2 molecules. So let us assume electron A, which is associated with the HA, and electron X, which is associated with the proton HX. And the energetically stable state is the one in which the electronic magnetic dipole moment opposes the magnetic dipole of its own nucleus. So this is how the spin of a proton and the spin of the electron A are actually paired. So they are of opposite spins. So such kind of interaction is said to be the Fermi interaction of the electrons, which will be with the two nuclei. Then comes, according to chemical bond theories, the electrons occupy with the opposite spins in the same orbital. So here comes a bonding between A proton and the X proton, and the bonded electrons which are there, two electrons, and those two electrons should be of opposite spins. That is according to the chemical bond theories. Hence, the spin of A electron and the spin of X electron should be paired. You can see that both these are actually paired. In similar case, in this, the spin of A electron and the spin of this C1 electron are said to be paired. These two are said to be paired, which are nothing but the bonded electrons between A and the C atom, carbon atom. And then next comes the C1 electron and C2 electron, which should be of having a parallel spins, as they occupy the degenerate orbitals, which is of degenerate orbital of the same atom, that is the carbon atom. So carbon atom has two unpaired electrons, and those two unpaired electrons will be occupying each subshells with a parallel spin according to the Hund's rule of maximum multiplicity, then on the pairing happens. So in that condition, the C1 electron and C2 electrons of the carbon atom will be resulting as a parallel spins. So after that, the bonding between the carbon atom and the B proton over here, again the electron C2 spin and the electron of this B spin should be paired. So at last when it leads to a most stable state, so the nucleus electron electron nucleus spins should be alternate. So this is how the nucleus spin, then comes the electron spin, then again the bonded electron spin, again the nucleus spin. So they remain in an alternate fashion, which will be leading to a most stable state. So the spins of A and X will preferentially be paired. So the expected combinations of these two proton spins are paired configurations, alpha beta and beta alpha. But in addition to these two configurations, their parallel configurations are also possible. They are alpha alpha, beta beta. Only the energy difference is so minute. Hence, both the configurations are equally likely to occur. So, when the interaction happens, four kinds of spin combinations are possible between the two hydrogen nuclei when they are directly bonded. So when they are bonded to a non-spinning nuclei, then the mutual magnetic uh, mutual magnetic influence will be happening through the bonded electrons, but not through the space. So this slide shows how the transition occurs between these spinning states based on the energy level diagram. So the effect of these spins on the spectrum shows how the peaks are obtained before coupling and after coupling. So the four possible spin combinations are shown for this AX system and in four different energy levels. And a convenient notation for this spins are represented as the spin states which are showing upwards are designated as alpha spin, and which has a value of plus half, and the spin state which are uh, pointing downwards are designated as beta spin, and which has minus half. So these are the spin states of proton A, and these are the spin states of proton X. So the transitions or the difference in the separation between the levels alpha alpha and alpha beta corresponding to a spin change of X alone. So alpha 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 beta shows that the spin of X alone changes and the A spin remains unaltered. Similarly, the separation beta alpha and beta beta shows the spin change of X alone. Hence, this is said to be the resonance energy of X. But in the next case, the separation between alpha alpha and beta alpha, alpha beta and beta beta, it shows the spin change of A, and this transitions are said to be the resonance energy of A. So the transitions between these various energy levels gives rise to two identical spectral lines, one at each of the chemical shift positions of X and A, which are designated as nu X and nu A. So these are the chemical shift positions of these two peaks. And this is observed when coupling is not taken into consideration. But when coupling is considered between the two protons HA and HX, on coupling, alpha alpha and beta beta are destabilized. So the interaction happens in such a way that the various spin combinations get interacted, and this alpha and beta beta will be further uh, raised by the energy of J by 4. Why? Because these are destabilized and that becomes unstable. Only the paired states are predominant and they are more stable. And in the same way, alpha beta and beta alpha, these energy levels are stabilized, hence the energy gets reduced by J by 4. So we could find the difference in energy levels on coupling, and thereby we will be expecting a kind of transitions between these energy levels. So the spin of X alone changes from alpha to beta, but spin of A remains the same in this first case. So two possible transitions of X are observed having different energies. So the transition from alpha alpha to alpha beta, the delta E value will be minus half. So energy is lowered by half J. Hence the spectral line which will be appearing below this mu X. And when the transition between beta alpha and beta beta, so the energy level difference is said to be half J. So energy which will be higher by half J. So spectral line appears beyond this mu X. So when we consider the similar transitions in A, in same way we will be getting two sets of peaks which will be raised, which will be decreased by half J value, and which will be half of the molecule will have raised half 1 by 2 J values with respect to the chemical shift positions. Since all the spin states are virtually equally possible, the probabilities of transitions occurring between any levels are actually identical. Thus, we arrive at an AX spectrum, a pair of 1:1 doublets. So each pairs are separated by a constant, coupling constant J. And the midpoints of the doublets are separated. The midpoints of the doublets are separated by a chemical shift difference. So this reminds us a chemical shift difference. From this diagram, we know that mu X and mu A, the difference is the delta value chemical shift difference. The same is observed here, mu X, mu A. The difference is the chemical shift difference. And with respect to mu X, two peaks, one which will be below mu X, the other one which will be above mu X, reduced by half J and increased by half J. So this is how the splitting happens due to the interactions of the various spin states of two protons. And that will lead to splitting of a single peak into a double peak. So this is for two types of nuclei. Then let us define what we mean by coupling constant. The distance between the centers of the two adjacent peaks in a multiplet is usually said to be a coupling constant that remains a constant. And the units for coupling constant, it is expressed in terms of hertz, otherwise cycles per second. And how it is denoted? It is denoted with a capital J with the superscript n and subscript AB. So superscript n is the number of bonds through which the interaction occurs, and subscript AB says the nuclei which are taking part in the coupling process. If in this case they are HA and HB. So J1, it represents that the interaction occurs through a single bond, and J2 occurs that the coupling of these two protons occurs through these two bonds, and J3 represents the coupling of these two protons through three bonds, which are separated by three bonds. So the coupling constant, as we discussed, the cause is due to the spin-spin coupling or spin-spin splitting. So here comes the magnetic interactions between the two nuclear spins of chemically non-equivalent protons, which are said to be NMR active, which are placed on adjacent or on the same carbon atom. So what is the significance of the coupling constant? We can extract more information about the structure of the compound as it is a measure of the interaction between a pair of protons, and J remains between 1 to 20 Hertz. So the factors affecting the J values, they are the gyromagnetic ratio of the two nuclei, then the distance between the protons, as we saw, the number of bonds separating them. If the coupling is if the number of bonds separating them increases, then the coupling will remain smaller. So coupling constant value will be small. The conformation of the molecule also uh, gives different J values. If the protons are in cis position, then the greater J value is observed. If the protons are in the trans position, then lower J value is observed. So here the magnitude and the sign of the coupling constant. So the J value actually attenuates rapidly with increasing number of bonds. That is, it reduces the J value, magnitude of J value reduces with the increasing number of the bonds. So for H2 molecule, which is separated, the two protons are separated by a single bond, J is found to be 240 Hertz. If two protons are separated by two bonds, then the coupling constant J2 is 12 Hertz, and for J3 it is 7 Hertz. Then if it is J4, then it will be 0.1 Hertz. So here the two protons which are attached to a single carbon atom on the same carbon atom, then such couplings are said to be genuine coupling. If the two protons are present in the adjacent positions, then they are said to be vicinal coupling. If the two protons are attached more than the three bonds, then that coupling is said to be long range coupling. And when we see the signs of the coupling constant, they are positive if the spin states in which the A and X nuclei have opposite spins, and if they and the J value remains negative if they have the same spins. So we know the nuclei which are close to one another will be producing the additional magnetic field on each other. So the picture on the left illustrates that the bonding electrons actually help in carrying that interaction over a longer distance. So the mechanism here involves the Fermi interaction of the electrons with the two nuclei and their mutual interactions due to the Pauli's exclusion principle. So here the nuclear spin of Ha proton will be interacting with the electron spin, which should be paired. Then these are the bonded electrons. So according to chemical bonding theory, they are remaining as paired electrons. Then comes the electron of the carbon, and this is also belonging to the same carbon. So they are remaining parallel. According to the Institute of Pauli's exclusion principle, they are remaining parallel. And again the bonded electron paired, and again these two electrons which are belonging to this carbon will again remain parallel. So in similar way, when the arrangement goes on, and finally when we look into the spin states of the protons, when based on their paired conditions or unpaired conditions, the J value will be resulting out. So in this case, if these two strings of HA and HX are found to be parallel, so negative J value, J4 will be negative, J3 will be positive, J2 again negative, and J1 will be positive. So we can conclude that the interaction will be between the protons, but not with the electron. The electron actually facilitates this interaction, but does not involve with the splitting effect. Only the magnetic moments of the protons will be influencing the magnetic moment of the other proton.